Wisconsin, University of Madison, Wisconsin. And then, as you know, that one of the most exciting discoveries of this century is the Higgs boson. And so she is going to tell us her personal perspectives of the brief history and the search for Higgs boson. Let's welcome Professor Wu.
I have to hold it. I don't have anything. Okay, I will give you a brief history of the search and also the discovery of the Higgs boson. So you all know in 1964, the paper from Professors Robert Brout, Francois Englert, and Peter Higgs. They proposed a new massive boson of spin zero to explain how elementary particles, the building block of the universe, get their masses. So on July 4, 2012, the discovery is announced at CERN, armed with 5 sigma significance independently from ATLAS experiment and CMS experiments. The Director General at CERN, Rolf Hoyer, says, "I think we have it. We have now found the missing cornerstone of particle physics. We have a discovery. We have observed a new particle that's consistent with the Higgs boson." So this discovery of the Higgs particle at LHC, announced on July 4th, was the result of 2 decades of works by the ingenious LHC machine physicists and by many thousands of ATLAS and CMS experimental physicists. They built and now operate the detectors. They defined and manage a computing system that distributes the data all over the world. And they created novel hardware and computing software to identify the most interesting collisions. And they wrote the algorithm that dig out the most pertinent event from the great morass of the data being recorded. It has taken a long journey to the Higgs discovery, more than 30 years. So before lab, which is I call pre-lab era, up to 1990, in 1964, crystal ball collaboration at DAISY, they think they have discovered the Higgs. So they were looking for upsilon decay, which is the bound state of BB bar, into Higgs plus a photon. And they see a peak in the photon spectrum, which corresponds to the Higgs mass of 8 GeV. And the signal significance is really huge, it's 5 sigma. And the rate is 2 order of magnitude larger than the standard model prediction. Unfortunately, at the end of the year, the signal disappeared, and other experiments did not confirm it. So then let's go to lab 1, from 1989 to 1995. On July 14, 1989, is the 200th anniversary of the French Revolution. So the first particle went around the lab tunnel, which is 27-kilometer ring at CERN. They choose that particular day, of course. So to look for the Higgs, you have E plus C minus go to a on-cell Z, which is centered at 91 GeV, and decay into a Higgs plus a virtual Z, which decay into a neutrino pair or a lepton pair. Now the rate is pretty reasonable. For 1 million Z decay, you can get 100 events for mass of 30 GeV Higgs. Here's a picture of Jack Steinberger, and he was a founder of the Atlas experiment at lab and the first spokesman. The reason I point him out is that he's really a promoter of physicists from China. Now I want to remind you about the sad story about SSC. The major construction started in 1991. The center of mass energy is supposed to be 40 TeV, and we can look for Higgs up to 1 TeV. However, the funding got withdrawn in October 1993, and that was it. But what is interesting now to look back, at LHC at 8 TeV, to produce a Higgs at 125 GeV, the SSC is only a factor of 5 higher at 40 TeV. So they could have discovered the Higgs 5 times faster. So at Lab 1, in the year of 1995, the 4 experiments together, Atlas, Delphi, L3, and Opal, each one has several million of CDK, and they have combined together to set a limit of the Higgs. It should be larger than 65.6 GeV. Now I go to Lab 2 era, which is from 1995 to the year 2000. So in 1986, there was an ICFA workshop called ICFA Workshop on Lab 200. The decision at that workshop, the workshop is for the decision whether CERN should build Lab 200 GeV or not. So in that workshop, we presented the results. It's E plus E minus at about 200 GeV center mass energy, produce a virtuous E, and it goes to Higgs and the on-cell Z. And the Higgs decay into BB bar, and the on-cell C go to neutrino pair, or 2 jets, or 2 leptons. So the result that I presented, summarized in the workshop, is that with reasonable accumulated luminosity, center mass energy 200. And you can see for Higgs 40 GeV, you can see a very clear signal with very little background. For the Higgs 60 GeV, it's similar. So this is what helped to make the decision to build Lab 200. So you can see, you can see that for Lab 2, the Z can decay into a neutrino pair, lepton pair, or 2 quark, 2B quark, and just 2 ordinary quark, and the B always go into 2 BB bar jets. So in the year 2000, Lab has tried to upgrade the energy 6 times, and each time a bit higher and higher, and chasing after the Higgs. So the final energy, although the design was 200, the final energy went to 209 GeV. And the sensitivity to the Higgs mass was 115 GeV. It's amazing enough, at that time, promising candidates start to show up. And late June, Aleph found the first candidate in the 4 jet events. 2 of them are B jets, and then 2 other jets. The reconstructed mass of the 2 B jet is 114 GeV. Then more events start to come. In early July, Aleph found another one, 115. In end of July, another one, 113. In August, Aleph found 110 and 115. So we were all very excited. And Aleph had published a paper on the axis of the events. And so we said that we have an excess of 3 sigma beyond the background expectation. So this is the beautiful event. So you can have 2 B-jet with a displaced vertex, another B-jet here, and then 2 ordinary jets. And the event is at 114 GeV. Then the other excitement came from L3. L3 said, we found 2 B-jets, and the mass of the 2 B-jets is 115 GeV. And then the rest of the event consistent with 2 neutrino pair, or without any other particle, basically. So lab was scheduled to shut down in September 2000 to allow the LHC construction. In early September, Delphi also found a 4-jet event. Based on all these events, Lab 2 was extended for 6 weeks. And then the event I just showed you by L3 make everybody excited. So on November 3rd, Lab Higgs Working Group make a request to the Director General for 6 to 8 months extension in 2001. However, the decision was to shut down in November after delivering of 11 years of great physics. We were disappointed, but at the end, the DG was right. So this is the CERN announcement of shutting down on November 2nd, was the last run at lab. So now let's go to the LHC era. On September 10, 2008, the first proton beam went around the LHC. Everybody was excited. But on September 19, an electrical fault triggered a major setback. There's a faulty electrical connection between 2 accelerator magnets, and this resulted in mechanical damage and released tons of liquid helium. One of the students from Harvard wrote in the logbook, saying no beam for at least a week. Well, it turns out that no beam for over a year. The first low energy beam circulate next time was November 2009. So So the path to Higgs discovery has several steps. One is the 2011 December, there was a council meeting. We had tantalizing hints of 3 sigma. And then on July 4th, Atlas and CMS, each experiment saw a 5 sigma signal. And then in March 2013, Atlas saw a 10 sigma. So there was no question we have discovered a particle. In March 2013, CERN has sent out a press release saying new results indicate the particle discovered at CERN is a Higgs boson. So since then, there are a lot of study about the spin, polarity, and coupling. So how do you discover the Higgs particle at LHC? So this is the LHC tunnel, and there are a lot of proton and proton collision. Inside the proton, there's a lot of gluons. So in fact, the Higgs is produced by 2 gluons interacting together. Now, the Higgs particle is not stable. The only way we can see the Higgs particle is through its decay product. So the most popular decay product is Higgs decay into 2 photons or 4 leptons through 2 ZZ going to 4 leptons. These 2 channels are particularly interesting because it has the best mass resolution. So the Higgs production is through gluon fusion. Now you all know the Higgs particle coupled mainly to heavy elementary particles. Of course, the heavier particles is the top part right now. So for this reason, that we have various processes can produce the TT bar. And for gluon fusion, which is the dominating production of the Higgs, it goes through a top part loop, produce the Higgs. So this diagram is called gluon fusion. Another competing production of the Higgs particle is so-called vector boson fusion. But however, if you take the fraction of vector boson fusion divided by gluon fusion, at 125 GeV Higgs mass, the gluon fusion production contribute 90% of the production cross-section in the LHC. So this shows the important role played by the gluon in the discovery of the Higgs particle in 2012. So gluon was discovered in 1979 at DAISY. So to search for the Higgs particle is not so easy. It's like looking for needles in a haystack. In Atlas, for example, up to July 4, 2012, we have a billion collisions. We analyzed 4.2 billion events. And at the end, we got less than 400 Higgs events that we can identify. So this is just to show you the various decay modes of Higgs. Higgs decay into 2 photons, Higgs decay into 2Z, each one go to 2 leptons. Higgs go to WW, Higgs go to tau, the fermion, Higgs go to BB fermions. Now I want to introduce a symbol, it's called P0. And the P0 is the probability that the background fluctuates to the observed data. In other words, you think you see a Higgs signal. What is the probability that comes from background fluctuation? So this is why we keep talking, we have a 3 sigma signal, 4 sigma signal, or 5 sigma signal. So for 3 sigma signal, the chances of 1 in 1,000 is a fluctuation from background. 4 sigma, 1 in 30,000 is a fluctuation from background. 5 sigma, 1 in 3 million come from fluctuation from background. So now we're talking about sigmas. So in the CERN Council meeting in December 2011, and both Atlas and CMS concentrate on the analysis, Higgs go to 2 photons, or Higgs go to 2Z, and CZ decay into 4 leptons. So you can see that for Atlas, for Higgs go to 2 photons, in this P0 probability has a dip at around 126 GeV, which is 2.8 sigma. And CMS had a mass very similar, 123.5 GeV, and also in the same decay mode, Higgs to go to gamma decay mode. It's a 2.3 sigma. Then look at the next decay mode. Higgs go to 4 leptons. And Atlas saw a 2.1 sigma at 125 GeV. CMS saw a 2.7 sigma, 120. Although the sigma value is not very high, but if you combine these two together, Higgs to gamma, and Higgs go to 4 leptons, you see that for Atlas, we have a signal at 3.6 sigma, and the mass is at 126 GeV. And for CMS, it's 2.6 sigma, the mass around 120. So you can see the 2 independent experiments. Each one has 2 different decay modes. Higgs go to gamma, Higgs go to 4 leptons. And you can feel that this is not a random fluctuation. So at that time, we feel that there's a tantalizing hint that we are seeing something. And these are the two, the spokesperson from Atlas, spokesperson from CMS giving the talks. So now I want to share with you the joy of discovery. With the result presented in the council meeting, December 13, 2011, there was now a small mass range for AT and CMS to hunt for the Higgs particle. They are around 125, 126 GeV. So therefore, there's a frantic activity for both experiments in the next 6 months to look when the new data are coming in. Now I want to introduce to you the concept of data unblinding. The data analysis is very complicated. It involves taking out the pertinence event from enormous amount of data being recorded. So what we do in each experiment, what we do is we devise a very complicated analysis, but you are not allowed to look at the data. You're just using Monte Carlo or whatever intuition you have. And then after your collaboration approves your method of analysis, then there's something called unblinding approval. Then you can unblind and you can open the box, look at the data. So this is supposed to be unbiased and fair. So you can see that because of December 2011 tantalizing hints, so CERN decided to skip the winter shutdown. Normally, CERN shut down in the winter because the power bill is too high. So at that time, there's a rapid accumulation of additional data, and everybody is very excited. So the unblinding was scheduled for June 2012. The month is selected because there is an international conference on high energy physics called ICHAP in Australia on July 5th. So now I tell you the experience of the joy of discovery. For CMS, a CMS physicist get together on June 15 in one of the rooms in a hot summer filtration plant to hear the first report after unblinding. There are two talks, one on Higgs to gamma-gamma. The other is Higgs to ZZ to 4 lepton. These two, as I said, have the highest mass resolution. So for both of these two decay channels, the signal from the new data were found again in the vicinity of the 125 GeV, where they saw 6 months ago in the December 2011 presentation. So the crowd cheered enthusiastically at the end of the two presentations. For Atlas, spontaneous celebration broke out in several groups when the data were first unblinded. In the afternoon of June 25, 2012, during a meeting, a graduate student presented the first successful combination of the data, leading to a result of 5.08 sigma, giving the Higgs mass 126 GeV. This presentation, of course, caused cheers ringing down the building. Another graduate student very soon confirmed these results. Now, why is 5 sigma so important? As I mentioned to you earlier, in particle physics, 5 sigma is considered to be the golden standard to claim a discovery. The CERN DG would not consider it a discovery unless we achieve 5 sigma. This means that the probability of the background fluctuate to look like a Higgs is less than, the chance is less than 1 in 3 million. So you can be pretty confident that you are seeing something. So on July 4, 2012, and also a day after in the conference I chaired in Australia, that July 4th was a great day for physics. This is it declared by a lot of people. So you can see that the two independent experiments, each with two channels. For Atlas, the Higgs to gamma-gamma had grown to 4.5 sigma with the data 2011 and 2012. And CMS, the Higgs to gamma-gamma, is 4.1 sigma. So they both are very close in mass, 125, 126. And for 4 lepton, similar thing happened. For Atlas, it's 3.4 sigma at 125 GeV. And for CMS, 3.2 sigma and 125 GeV also. So if you combine together, for Atlas, we have combined the gamma-gamma 4 lepton together. You see the 5 sigma at 126.5 GeV. Again, I remind you, 5 sigma means the chance of having the background fluctuate to the signal is 1 in 3 million. And CMS have 4.9 sigma and at 125 GeV. So this is it. And Tevatron also presented the result. Their analysis is Higgs go to BB bar, and they see 3.1 sigma. So they discovered the Higgs boson on July 4, 2012. At that time, we do not call it, we call it Higgs-like particle. On the day of the announcement of discovery of July 4, 2012, the auditorium at CERN was locked purposely until 9 a.m. Half the seats were reserved for VIP. In order to encourage all my students and postdocs to witness the scientific event of the century, I promised them each one get $100 from me. Whoever lined up the night before outside the auditorium and slept on the floor. And they all slept on the floor, and they all got in the next day. So this is how the auditorium looked like. So the poor student and postdoc who slept overnight are at the back, and the VIP are in the front. There are 4 former DG, 1, 2, 3, 4. Where are you, Carl Rubia? Where are you? You can, I can? I'm joking. So at the end of the CERN seminar on July 4th, I went to shake hands with Professor Higgs. I told him, I've been looking for you for over 20 years. He said, now you have found me. In fact, it had taken me 32 years from 1980 to 2012. So in the afternoon after this announcement, the Higgs Working Group in Atlas here has a celebratory drink. Everyone was watching the corks of the champagne bottle flying up to the ceiling. And we have each bottle represent 1 decay mode of the Higgs. So this is the cover of the physics letter of the discovery. This is the peak by Atlas, and by CMS, gamma-gamma. This is the combined significance of Atlas, and it was published in September 2012. So the publication is slightly different from the July 4th announcement, because in Atlas, we have included Higgs to double channels. So we have obtained 5.9 sigma, where CMS remained 5 sigma, and the mass is 126, 125. So now I want to show you how the Higgs to gamma gamma grow as time goes on. So you can see the peak grows as we have more and more data. That's the Higgs to gamma gamma channel. And the next one is a Higgs go to 4 lepton. Again, the same thing. So you need patience. So you see, this is the peak. Those are background. Oops. I stopped it, I guess. No. Okay, so on March 5th, 2013, the New York Times front page has covered the Higgs story. The heading is called Chasing the Higgs, Struggle and Finally Triumph in the Search of Physics' Most Elusive Particle. So you see 2 CMS spokesmen and Atlas spokesperson, Professor Higgs and myself. So in October 2013, the Physics Nobel Prize was announced. And we have Anglais and Peter Higgs here. The citation is for the theoretical discovery of a mechanism that contributes to the understanding of the origin of mass of subatomic particles, which recently was confirmed through the discovery by the Atlas and CMS experiment at CERN, the Large Hadron Collider. The rumor I heard was that the announcement of the Nobel Prize was delayed by 1 hour. During that time, there was still discussion going on whether CERN should be included in that prize. So the new result recently, in June, you can see that here's the final peak for the gamma gamma for Atlas and final peak for the 4 lepton in CMS. And the other one was a 4 lepton from Atlas, gamma gamma from Atlas. And this is gamma gamma from CMS and this is the Higgs peak 4 lepton from CMS. So the thing is that in the meantime, we have settled on the mass, 125 GeV for both experiments. And we have determined that the Higgs is a scalar particle and excluded the Higgs being pseudoscalar, excluded spin 1, spin 2. And the coupling to gauge boson is determined to 10%. So in the meantime, Higgs go to the fermion, tau tau and BB have been established by Atlas and CMS. So Professor Dave Charlton will give a talk on more new results tomorrow. So now, since this is education conference on physics education, I would like to address the question, how do graduate students benefit from participating in the Higgs discovery? They work at CERN in an international environment, and they have a chance to participate in and witness major discovery in physics. They learn to solve problems under tremendous time pressure. They cannot be slow. They are constantly in a friendly competition with young physicists from many countries. So this kind of training is especially important in the international global arena. I'll finish soon. So now let's look forward. The particle we discover, before the discovery of this particle, there are spin 1 and spin half particles. The Higgs boson has spin 0. This is the only new particle, not only a new particle, but a new type of elementary particle. For this reason, the discovery of the Higgs is most important step forward in the physics in the last half a century. Carl Rubio is here. So I should include W and C. So he opens a new era of physics. Can we make a guess? The guess is that we should have other spin zero particles. And can we guess that there are spin zero quarks, spin zero lepton, and how do they behave? They are pretty heavy because the C mass with the C width constraint. So we can see that maybe there are spin zero quark and spin zero lepton, and it's like as many as ordinary quark and ordinary lepton. Then it's a dream come true if it happen, that the symmetry between fermion and bosons. Okay, the last transparency. The look forward is run 2. Run 2 starts in May 2015 and run until May 2018. Center mass energy will go from 8 TeV to 13 or 14. And so since the cross-section is higher, we will expect in run 2 have a factor 10 more Higgs events than we have now. So the conclusion is we have the Higgs. It has been a long journey to the Higgs discovery in a truly international effort. This particle opened up a fabulous new era of particle physics. The glory of the Higgs discovery should be shared by the entire Higgs community, which has been chasing after the Higgs for over 30 years. So we should congratulate to everybody who ever looked for the Higgs. I would like to thank Professor K.K. Hu for inviting me to give this presentation.
Thank you, Professor Wu Xiaolan, for giving this exciting story of the discovery and search for Higgs bosons.
Don't give me that.
We are running out of time, but I think Professor Carl
Yes, I'd like to
Rubio,
add a few comments on this history of the Higgs particle, which I think it's a long story. In particular, I like to say that indeed the possibility of discovering the Higgs particle at LEP was the real question I like to mention. When LEP was built by Herwig Schopper. The machine was supposed to reach the Z0. The Z0 was discovered, was a very nice source of information. And then when I came in, the question was to bring LEP into superconductivity. The superconductivity development was done during my times. And the situation was that at the time of the LEP, the magnetic field was calculated of 130 GeV. Remember, the Higgs is 125. 130 was the energy which you could do magnetically. And at that time, I also contributed by introducing the superconductivity for LEP. And we put enough cavities there to reach the 130 GeV field, which was the one which was possible magnetically. So, in fact, there was a real possibility to discover the Higgs from LEP. And it was my successor, Chris Llewellyn-Smith, which decided to scrap the last segment of radio frequency cavities. And this was why, indeed, the Higgs had to wait until the LHC to come out, otherwise it would have come out of the LEP very easily because the field was there. And both Schopper and myself were of the opinion that you could go to 130 GeV, therefore beat 125. The second remark I'd like to make has to do with the fact the Higgs mass is so low. At the time in which we had the SSC versus the LHC, I remember there was Steve Weinberg who was claiming that the LHC was not sufficient in energy in order to be able to measure the Higgs with it, because the Higgs particle at that time was assumed to be close to 1 TeV, or mass not very low as it is. In fact, it's remarkably low, 125 GeV. It's really the lowest you can have. And then it turned out that even the LHC would not be able to do it, and you had to have an SSC. Indeed, reality has been very different because with half of the energy, the LHC had plenty of energy to do the Higgs particle per se. Which brings in another questions about theorists always claimed that the Higgs was associated with a so-called no-fail theorem, that you were obliged to have supersymmetry because without supersymmetry, the mass of the Higgs will just move itself to infinity or to very high masses. Some theorists explain better. But indeed, this is not the case because we don't see any supersymmetries, at least so far. And maybe theorists have lost their imagination for supersymmetry, and the Higgs is there. This is so because Higgs mass is very low. If the Higgs mass would have been another 50 GeV higher, it would end up into the no-fail theorem area, and that area, it would have become unstable because of high order corrections, and then it would have been, if no supersymmetry would have been there, no Higgs would have been found. Now, so therefore, the question of supersymmetry is very much connected with the discovery of Higgs, and nature seems to have decided that. Now, the final comment I'd like to make on the number standard deviation that Saulan has been so carefully describing, let me here remind you another very important contribution for a very important Chinese physicist, which is T.D. Lee, T.D. Lee has calculated once how many times the 3 standard deviation effect was right and how many times was wrong. And his estimate, 50% of the 3 standard deviation issues turned out to be wrong, as he was given the example, for instance, from the Daisy story about that peak and many other things. So that world of standard deviations is really a theoretical number. In reality, physics is much more complicated than that. And it takes much more than 3 standard deviation in order to assess the validity of a result. This is a real experimental proof. Thank you. I finished that.
Thank you for the comment.
This is excellent comments from Carlo. I think that's, I wish you had pushed harder because I would have liked to find it in lab. I'd be younger. But about the sigma, that's true because we have 2 experiments, CMS, Alice, each one have 5 sigmas. So.
Yeah, I saw another hand raised earlier, but otherwise we will go to lunch. Yeah, let's thank Professor Wu Xiaolan again.